Dr. Clancy James, welcome to the show.
Thank you very much, because we do know what cosmic rays are now. The equivalent of dropping a brick from about a metre, a collapse of supermassive magnetised rotating stars, the highest energy cosmic rays. And so you make a plot of this, inconsistent with this multi-wavelength data. And yet we saw a neutrino coming from it. And yes, please Google all that.
But you lecture electromagnetism, the second year unit, which is a very fundamental classical branch of physics. So how often do you apply these classical branches of physics to your research?
Well, let's see, I guess the best way to answer this question is by describing one of my claims to fame. So I mentioned earlier this project of using a radio telescope to detect cosmic rays. And the way this happens is you have a cosmic ray hit the top of the atmosphere, converts its energy to mass, as anyone who knows E equal mc squared will tell you, and you get a cascade of millions of secondary particles through the atmosphere. Many of these are charged particles, and they produce radiation, and that comes in the form of a few nanosecond bursts that can be detected by radio telescopes. In around the 2000s, people got more sophisticated instruments, able to perform like well-calibrated measurements, right? And they were able to get a good experimental idea of what the signal looked like. So then the question was, well, how do we use this signal to reconstruct what the particle cascade looks like? So people did that, and they had a bunch of different ways to do that, and none of them worked, right? None of them worked out, or nobody could reproduce the emission from the particle cascade to the ground. Now, when I say particle cascade, that sounds complicated. What it fundamentally is, from a microscopic point of view, is just a bunch of charges that move. Right? That's pretty classical electromagnetism, right? What are the electromagnetic fields from a bunch of moving charges? You need to add in a bit of special relativity in there, but that's also first year physics. So all you need to do is combine special relativity and Maxwell's equations of electromagnetism, and then you end up with calculations for the radiation that you expect from these particles, right? From a macroscopic perspective, it's even simpler. What is the macroscopic explanation for a bunch of moving charges? Currents, right? It's just a current that starts here, grows in magnitude, and then peters out, right? And so the way that you calculate radiation from these currents is not quite covered in second year electromagnetism. We basically stop the course usually at the chapter right before these calculations, but it's very close. So I came into this field in around 2009, and one of the tasks that I was sort of given was to figure this out. And so one of my I think it's my second to most highly cited article, is one where we solved the problem, right? We worked out what was going on. And the solution to that was then put into and it's a relatively simple solution, was then put into a more complicated simulation program that simulated the particle cascades themselves and includes particle physics. And this program is called CoREAS. And we then went from a situation where no one was able to predict the emission to when a radio telescope called LOFAR, using this CoREAS program, was able to perform the most precise reconstructions of these cosmic ray ash showers ever, right? Improved upon previous measurements by a factor of about 4, right? And so this technique is now, and this program is now used internationally for about a dozen different experiments. And at the end of the day, this was just second-year electromagnetism being applied to this problem. It's just that you had to have a pretty good understanding of the nuances of what's going on to do the calculations. But yeah, so I guess that's an example of, where this came in. And in our current project, at the moment, I'm actually looking for students to work on the next stage of these calculations to get the higher level of precision and actually check that this lovely solution we came up with and that was published in 2011 is actually correct enough for the observations we expect to perform. My guess is that it isn't.
Something else you do as well that's quite similar, I suppose, because it's still a ray, effectively, much like cosmic rays, is fast radio bursts. So what are that?
That's an excellent question. What's next? Again, this is something where we don't fundamentally know the answer to, although we are getting close to it now. So the definition of a fast radio burst is fairly self-explanatory. It's something that's fast, right? Typically occurs on millisecond timescales or less, and it's a burst of radio waves, right? And it's a burst in the sense that it's not very predictable, unlike pulsars, which produce bursts of radio waves but with regular periods. fast radio bursts, or FRBs, they do have some interesting structure, and they do sometimes produce some progenitors will produce multiple bursts in a sequence, but there's no sort of predictive way to estimate when they're going to occur. So this was something that was first observed in data from a radio telescope in Australia. The data was taken in, I think, 2001, but it was only reanalyzed and found in about 2007. And the extraordinary thing about this first burst, which is called the Lorimer burst, was not just that it was bright. I mean, it was very bright. That was extraordinary. But it had something known as the dispersion measure that indicated that it came from outside our galaxy. Now, what's a dispersion measure? Well, we know that light travels more slowly through glass and water than it does through air, right? And even though the gases in the universe are pretty tenuous, right? The universe doesn't have very dense gas in it. It does have some. And this means that the radiation that we see in radio ends up being, actually, yeah, I might use a diagram here in a sec. The radio wave radiation we see travels at a slight, tiny fraction slower than the speed of light, right? Because the universe isn't quite a vacuum. Very close to being a vacuum, not quite. So, yes, I think we're getting the typical diagram of a dispersion measure here. So what you can do... Now, the other important thing about this is that the index of refraction, the speed of travel, depends upon the wavelength. So what that means is blue light travels at pretty much the speed of light, and at lower frequencies, the speed is reduced. So as we've got this lovely diagram here, we should see that if the radiation is travelling to the left, then the blue part, the higher frequencies, are going to arrive before the lower frequencies. So if we just measure that, what that means is if you draw a plot like this, where this is your frequency and this is your time, and time is increasing that way and frequency is increasing this way, you see a burst that looks like this, right? It's got that characteristic slope, and the time goes as your frequency to the -2, like that. So at low frequencies, and this is your time delay, right, I should say, because of course there's some absolute time in there. And so depending upon this slope, and you can measure how much gas these bursts have gone through. And we've got some reasonable idea of how much gas there is in our galaxy. And this burst was seen to have gone through far more gas than we can possibly explain through the interstellar medium in our galaxy. In other words, it's extragalactic. And as soon as you say that something's extragalactic, it must be really far away, unless it happens to point back to the Large Magellanic Cloud, which it didn't. And then you suddenly see something that's really bright when we observe it, and it's come from somewhere in the distant universe. And so these are incredibly energetic bursts of radiation. So that's fundamentally what a fast radio burst is, a short burst of radio waves that is extragalactic in origin and hence extremely bright. Now, we've seen a whole bunch more of these since. We actually, yesterday were awarded a prize, our collaboration craft, for the best paper, or the most significant paper in the journal Science for all of the previous year. It's not a Nobel Prize, but as far as science goes, it's probably the next level of prize down you can get for significant research, this kind of prize. And so that was awarded for actually detecting one of these bursts and being able to then reconstruct the arrival direction to point to a galaxy that was then about of order a billion light years away, a few billion light years, actually, and came from the distant universe, and then work out that fast radio bursts were coming from galaxies, but they were coming from really far away.
And in a very similar project, I think it was just before the project you mentioned?
Just after.
Just after, okay. The fast radio bursts were used to measure the baryonic matter in the universe. Mm-hmm. So how is that possible?
So the simplest way, actually I want to take a step back at some point, but the simplest way to measure that is simply to say, I mentioned that this dispersion measure is proportional to the amount of gas that it's passed through. Essentially, it's ionized gas. It measures the free electrons, right? So you've got ionized gas is simply you've got the positive atoms here and you've got the electrons that are then free to move around and respond to electromagnetic fields as they will, as opposed to being tied to an atom. So it measures the total amount, it's actually the free electron density, But we know that in the universe we don't find large areas where there's large negative charges over here and large positive charges over there, because the Coulomb force is really strong. So if you know that this dispersion measure is proportional to the amount of gas that it's passed through, then as soon as you see an FRB, you know the total electron density. Now what you then do is, for every FRB, you take a telescope like ESCAP and you work out exactly where it came from using radio interferometry. It's a technique that if you do anything in Cairo, you'll find out about a lot. You then take an optical telescope and you point the telescope in the direction. So the telescopes we were using were things like the Very Large Telescope in Chile. It's a European telescope. Keck, which is an American telescope on Hawaii, and also the Hubble Space Telescope. You point the telescopes in the direction we see these bursts coming from, and you measure you see the galaxies, right? And you need a powerful telescope because some of these galaxies are really far away. You then work out what the redshift of these telescopes are, right? Which gives you a distance. And the expansion of the universe, we know, relates to how far things are away. You then do a plot, and I'll pick up the magical pen and do another plot that looks like this. Here we have redshift, and here we have DM, right? You then say, okay, let's imagine we measure a burst from the nearby universe. Well, let's imagine that we measured a burst from the Large Magellanic Cloud, right? Very nearby galaxy. The redshift of that's effectively 0, right? It's just there. But it's going to have a non-zero DM, right? It's going to have a DM somewhere there because, of course, there's galactic gas between us and the Large Magellanic Cloud, and the LMC itself has gas. You then say, okay, let's imagine that we measured a burst from a nearby galaxy that's, let's say, 100 megaparsecs away, which cosmologically, that's actually pretty close. Even though 100 megaparsecs, that's 300 million light years. It's not super close, but it's cosmologically pretty close. And then you say, well, that gets a bit more gas, so we might measure a point up there.
So
now
would
we
that
measure
be like
something.
Andromeda distance, or?
Andromeda's only a couple of megaparsecs.
Okay.
So Andromeda galaxies that are sufficiently close, the redshift is meaningless for them because there's always some motion of the galaxies about their own, like the gravitational pull of their neighbours, right? And the local supercluster of galaxies. And so it's generally only on scales of tens to hundreds of megaparsecs that the redshift actually becomes significantly meaningful. Beyond that, it's dominated by the peculiar velocity of galaxies and which way they happen to be going. And so you measure another point there, and then you measure some more galaxies in a very distant universe. Right? Now you notice the way I'm drawing this line, you've basically got two features. You've got a slope, an intercept, and some scatter about it. Right? Effectively, what you're aiming to do is measure these three features. The intercept is the average contribution to the dispersion measure from the Milky Way and our halo, because when we talk about the Milky Way, we think of, the stars that you can see as the Milky Way. Or let's put it this way, if you've ever been outside of a major city into a properly dark sky, then you'll see the Milky Way and this contribution of very many stars. But actually a lot of the gas we see in the Milky Way, the ionized gas, well, we don't actually see that because it's ionized, light generally passes through it. Right? But there's also a fair bit of gas that should live sort of outside our galaxy in a halo, right, around it. That's very diffuse gas and it's very difficult to detect. But we're sure it's there to some extent, we just don't know how much.
So we usually see an image of a disk of a galaxy. Are
Yeah.
you then saying that there should be kind of a sphere around that?
Yeah, spherish. Right. So the actual so a galaxy is mostly dark matter, right? And then the baryonic matter has then fallen into this dark matter well, right? And clearly because it's dark, we don't see the dark matter directly. We only infer its existence through the actual velocity of the baryonic matter, right? Baryonic matter being normal stuff, right? Atoms, protons and neutrons. So this halo should exist in an approximately spherical-ish form around our galaxy, and that's going to consist of fairly hot, diffuse gas that's pretty difficult to detect. Then there's also going to be a contribution to this intercept, right, from the host. So naively, this intercept here will have two parts. There'll be the local part, so that's, Milky Way, that's us, and the host galaxy. Because, of course, whatever this FRB is, it's sitting in more matter And so the burst to get to us has got to get out of its local contribution and then to us. Then you say, well, what's going on with the slope? Well, I don't know if you've seen one of these typical filamentary spiderweb structures of the universe, where people look at the large-scale distribution of matter in the universe,
we could find
and it's
one
called
now,
the cosmic web. So, if we look at this, you'll see that there's this filamentary structure, and most of what's there is actually these large empty areas called voids, right? And these are large areas where there's no overdensity of dark matter, and so there's been no clumpiness. Baryons in the universe have not congealed to form galaxies, right? There's kind of nothing there. And so this occupies most of the volume of the universe. Except, and by the way, I should emphasize that when you look at these simulations and these plots, this is all dark matter, right? The baryonic matter shown in there is mostly visible, would be visible only in galaxies that sort of have formed in these overdensities of dark matter.
So
however,
talking these
are voids. Yep,
areas.
these things are the voids, and then this big bright thing might be a supercluster of might be where a supercluster of galaxies would live, for instance. Now, as you can imagine, an FRB that lives at, I don't know, some point here, right, and it was emitted there, and let's imagine that the Milky Way lies in our local group of galaxies here, and maybe that's the M87 cluster of galaxies. And then this FRB has to get to us by going through here. Now, even though I've talked about these voids, they still have some very, very tenuous amount of gas in them, right? And in fact, when people try to add up where all the matter in the universe lives, the normal baryonic matter, only about 0.5, maybe only about a tenth of it, right, of the baryonic matter in the universe, maybe less, I might be getting my numbers wrong, this is not my field, lives inside galaxies, right, and stars, and is easily visible. Because these voids, even though they have very diffuse gas in them, they're huge, right? Like the volume that you just drew a circle around there, that's, think of it as a sphere where the radius of 100 million light years or more, right? And so when I went back to this diagram of, let's see, can we go back to that sketch I drew?
We can, when I get this over here.
Oh, there we go. Yeah. Oh, perfect. We can show both of them side by side. So this slope here is essentially the extra dispersion measure that this burst is picking up as it travels through all the matter along this line of sight. And you can clearly see that, the further it goes, the more dispersion measure will be picked up. And so this was the first time we were actually able to directly probe the density of this matter in these voids, right? Because if you point a telescope at these areas, you see nothing. You see the bright stuff behind it. So this is really how we were able to sort of weigh the universe, is the phrase. It was there. And the great thing about that is the results were also completely consistent with our cosmological estimates. So when people run these simulations and they compare the results of these simulations with, let's say, expectations for the cosmic microwave background radiation, which also gives you some measure of the structure of the universe, you can infer what the total baryonic matter density of the universe should be, right? But when we look around us locally, because we can't see the gas in these voids, and we try to sum up the contributions, we don't get there. But using this method, we did, right? The slope is completely consistent with our expectations from Big Bang cosmology, which is also incredibly disappointing. But because, of course, whenever something's consistent, well, yeah, science likes surprises. The other thing I want to point out about this is that I drew this scatter, right, about this line. And you'll notice that there's all this filamentary structure in the universe. So one thing that we want to do, and that we haven't been able to probe yet, but we will be able to do with more FRBs where we know the host galaxies, is look at this scatter and see to what extent ionized gas is being shot out from galaxies, into the regions around them, right? So this is a process known as feedback. So whenever a supernova goes off, it blows a bunch of gas, blows out a big amount of gas in its host galaxy. And sometimes this gas will have enough energy to actually escape the galaxy. I also talked earlier about active galactic nuclei shooting jets out into galactic space. Well, sometimes that's sending ionized gas, into the regions around galaxies. And there's also sort of finer details about this halo, right? How big are halos? Because as this halo of gas around the galaxy gets larger, then this fast radio burst coming along here will intercept more of the halos. But if the halos are larger, then the gas is going to be more diffuse. And so you're going to have less scatter, right, you're going to have a more constant sort of, you'll have less scatter about this line. Whereas if these halos contain a lot of gas, but they're small, then you're not going to intercept many of them, but when you do, it'll be a big extra contribution. So the next kind of steps that we want to do in this research is to actually study this sort of filamentary structure of the gas and feedback and how matter gets ejected from galaxies using fast radio bursts. But as you might be able to tell from this plot, at the moment we only have maybe now it's about 20 localized fast radio bursts with host galaxies, and we're going to need a lot more to be conclusive about that research.
So what problems might fast radio bursts solve? Because obviously we don't know what they are, but we know that they exist. We know we can weigh the universe with them. So what else might they be able to do?
In terms of the problems they might solve, I already mentioned this idea of feedback, right? Probing how gas in galaxies then gets ejected. And this is also related to a problem which is known as the missing satellites problem. So when people do cosmological simulations, right, what essentially happens, and this is a very short version of cosmology, is in the early universe, there's random fluctuations and the dark matter starts clumping together. Normal matter doesn't, because there's a lot of radiation about, and as soon as you get an overdensity of normal matter, it heats up and wants to expand again, right? Dark matter doesn't face that problem because it's dark, it doesn't interact with radiation. So the dark matter starts clumping, and then eventually the dark matter clumps are sufficiently big, and the universe is expanded so the radiation is no longer intense enough to stop normal matter falling into these halos. So what you end up with, this is what was shown in that lovely purplish diagram earlier, is a whole bunch of dark matter clumps, and then you expect galaxies and normal matter to do things in them, right, to get dense enough in them to form stars and galaxies. However, when you do those simulations, you expect a very large number of smaller galaxies, right? For every galaxy the size of the Milky Way, you might expect 100 smaller ones. And yet, when we look around galaxies like the Milky Way, we do not see this very large number of small satellite galaxies. Sure, we see some satellite galaxies, but not many. And one of the theories as to why we might not see so many is because as soon as there's a little amount of star formation in one of these galaxies, the first supernova goes off and then blows out all the gas, right? Then, these galaxies are small enough that when there's an energetic event like a supernova, the gas gets hotter and then just expands out of the galaxy. Unlike the Milky Way, which is big enough that a supernova goes off, it goes blue, and then the gas comes back due to the gravity. And so when I was talking about the feedback problem, that is related to this missing satellites problem, right? And that would be fantastic to solve. So that's one example. Another example is simply what is producing the bursts themselves, right? I haven't talked about that very much, but these are extremely bright bursts of radiation. Now we think that these are being produced by objects called magnetars. So to go back a few steps, a neutron star is when you get a supernova goes off and the matter in the core is crushed by gravity so that you essentially have it being 100% neutrons. I could go on to a topic about strange stars and the equation of state of very dense matter, but I'm not going to do that. That's something we will cover actually now in the third year nuclear particle physics course very briefly because it's extremely complex, but anyway. And then you could say, well, you've got a neutron star, this is formed from a collapsed star. We know stars have magnetic fields. When you take a magnetic field that's this big and you compact it, it gets stronger. And so we find that some of these neutron stars have incredibly strong magnetic fields, right? And the strongest ones are things known as magnetars, where they have magnetic fields of around 10 to the 11 Tesla, right? 10 to the 15 Gauss. Gauss is an outdated unit that for historical reasons we still use. So the energy density of these fields is incredible. I forget exactly what it is, but it's just ridiculous. It's more than one atomic bomb per cubic centimeter, right, of energy density. And so we think that these objects are what's producing the majority of the fast radio bursts that we see. In particular, because we did actually see a magnetar in our galaxy simultaneously produce a burst of X-rays and a burst of radio waves. Even though that burst was incredibly strong, it was still 1,000 times less strong than the FRBs that we have seen. So these are sort of some of the ideas of the problems that we'd like to solve.
And how are students prepared by the physics degree at Curtin to contribute to these solutions?
To ultimately solve these high-level problems. You're not going to come with an undergraduate degree and then suddenly do that. However, if you look at the physics that's actually required to solve these problems, there's two aspects. One, you need a pretty good overview, right, of the of what's going on, right? You need a broad overview of the kind of physics involved. And this does range from courses like electromagnetism to nuclear and particle physics to cosmology and high-energy astrophysics, right? So the undergraduate courses should give you a fairly broad, sufficient background to understand broadly what's going on. Now, as I sort of mentioned earlier, with, say, second year electromagnetism, you're not going to suddenly go from that to modelling the relativistic plasma physics that's required to understand what's actually going on in the field of a magnetar. Right? What fundamentally happens is that the undergraduate degree should give you a good base on which to, A, find out that these problems exist, right? To actually go on and solve these issues. You need to know they're there, right? You need to have some idea of what's going on. The next thing you need to know is, what is research really like, right? I mentioned earlier about the fact that research is not like an exam. It's not like an undergraduate course. It is, however, like a research project. And so I think a really key part of the undergraduate course here is both the summer scholarships but also the undergraduate research projects in third year, right? To give you a taste of what research is really like. Because at the end of the day, if your goal is to have the most secure job possible or the job that pays the most highly, don't do research, right? I mean, you get good, I'm not going to complain about the salary that I get, right? It's pretty good. And, it's a good job, but people who do research should be doing it because they're fundamentally fascinated by it and motivated by these interesting things, right? If you want to just get a basic secure job, go into teaching, right? We need good teachers to get students enthused about these things, right? So I think that's one aspect of how you're prepared to do it. As far as the detailed contributions go, that's really when you need to then go into an honours and a PhD. At the end of the day, to be able to call yourself a scientist or a researcher, you need to have done a Doctor of Philosophy, right? A PhD, which means that, you've got your undergraduate, then you've got an extra year for honours, and then typically 3 and a bit years for a PhD. And that entire process is really to train students to become independent researchers and solve fundamentally new problems. And it's really at the time of your honours that you start to specialise, right? So, for instance, you might start to say in honours, right, I want to tackle how magnetars might produce fast radio bursts, right? And then you're going to have to start specialising from there. And so, for instance, the kind of physics that you need to understand to tackle that kind of problem, relativistic plasma physics and electromagnetism, is quite different to the large-scale cosmological simulations that you would need to understand feedback, right? It's a very different topic. Now, over the course of your career, you might be able to do both, right? So in my career, I've worked in high-energy neutrino astrophysics for 6 years in Germany, but also the radio emission of cosmic rays, for several years, and now I'm working on fast radio bursts. But it's now been, almost 12 years since I was awarded my PhD, and typically you would start out going in one direction. That's sort of how our undergraduate degree is structured, with the aim of then eventually being able to have people, solve these problems.
So the undergraduate degree kind of provides you with the fundamentals that you need, and then it allows you to decide whether you'd like to continue from there.
Yeah, I think so. And I think one other thing, and this is where there's been a lot of emphasis recently, is that if you think about who is a researcher, you think of a professor, right? A full-time, professor at a university. How many jobs are there for professors compared to the number of people doing undergraduate degrees in, say, physics, right? And the answer is there's a heck of a lot more people doing undergraduate research than do professors. So another emphasis of the undergraduate degree is really on the fundamental problem-solving skills, which can then be applied to other problems in general, right? Whether or not those problems are in research or in industry. Right? And actually, in general, one of the reasons why the Western Australian government funds ICRA, right, which is the International Centre of Radio Astronomy Research, is because they're aware that the kind of skills that you get as an astronomer can be useful in jobs outside of research. But nonetheless, and I think this is something that undergraduates should be aware of, right? You should absolutely come into a physics degree thinking, science is great, I love it, I want to do it. But don't come into a physics degree thinking, I'm going to become a professor, and if I don't, it's the end of the world for me, and that's the only thing I want to do in life, because it's just difficult. Right?
Well, that's all we've got time for this episode, so thank you, Clancy, for agreeing to be here today.
Well, I certainly suggest that if you're ever interested in interviewing any other researchers from CoREAS, I'll encourage them to be part of this. It's actually a great experience.
If you want to see more content like this, make sure to hit the subscribe button and ring the little bell icon, or if you want other people to see our videos, please like, share, and comment below.
And until next time, stay curious.